Exercise 4E, graphing cubics. So today we're learning about graphing cubics. What you need to be able to do is recognize graphical features of various polynomials, sketch cubics by looking at the equation, recognize points of inflections and turning points, and then being able to actually graph the cubic onto a Cartesian plane. So in terms of graphing, the cubic function has this particular form. Some of them have this particular form. And with this form, we specifically have a stationary point of inflection, and that occurs at hk. So it kind of looks like the turning point form of a quadratic, except there's a to the power of 3 instead of power of 2. And then our key point is at this point hk, which is a point of inflection. This particular form will have one x-intercept, and the long-term behavior is dependent on the sign of a. Now, what we mean by that is whether it's a positive cubic, so that would be a is greater than 0, or a negative cubic, where a is less than 0. So other forms of the cubic is in factorized form. So this is where they're going to have multiple x-intercepts, and that's where you get that wave kind of shape like this. So in this case, this cubic here has three x-intercepts, three distinct x-intercepts. It cuts the axes 3 times at these particular points. Uh, Sometimes we'll have one of those factors that is a double factor, it's to the power of 2. And so what happens is that it actually touches the x-axis at that point and it turns around. So we're going to go through all the scenarios now in terms of what these cubics look like. So we'll start off with our first one here. As we spoke about, this is the stationary point of inflection form. So if we have a look at here, this is at the point hk. So obviously this one's at 0, 0. So this one would just be as y equals x cubed, or there might be an a if there's a dilation factor there. This particular cubic, as you can see, is to the power of 2, which means it touches the x-axis. So this point here would be A. You can see it touches and then it turns around. So up, touch the axis, and turn around. Now this particular cubic has 3 intercepts, so we'd have A, B, C, ignoring the negatives and positives, but that would be your 3 points, and it cuts the axis at 3 times. So those are all the situations that we can get with a cubic. So whether you have a factor that's to the power of 3, the power of 2, or all of them to the power of 1. So when we sketch, we need our x-intercepts, y-intercepts. Later on, we'll also be needing turning points, but for the sake of this exercise, we won't be doing that in this case. So sketch this particular graph. The first thing we're going to do is make y equal to 0 to find the x-intercepts. So if 0 is equal to 2, x minus 1, x minus 4, x plus 2, you can use the null factor law to discover that x is equal to 1, x is equal to 4, and x will be equal to negative 2. So those are going to be my 3 x-intercepts. Now for the y-intercept, we just need to make x equal to 0. So we'll go y is equal to 2. We'll have 0 minus 1. I might just write it right away as negative 1, negative 4, 2, which will equal 16. From there, we can go ahead and plot this on a set of axes. And I can put in the points. So this could be negative 2, this will be 1, and this will be 4. So just trying your best to keep it to scale. So we'll go ahead and put our cubic in as best as we can. And then this point here, it's not necessarily the turning point, but it's just that it happened to be drawn like that. Will be there, negative 2, 0, 1, 0, 4, 0. There we go. And here we have what our cubic could possibly look like without actually knowing what the turning points are. Right, next example, part B, we can see that there's actually something very special happening here, which is the fact that one of our factors are to the power of 2. And so if it's to the power of 2, we know that this factor will be a turning point. So x equals 1, we're going to go ahead and touch the axis and we'll be turning around. And that's the second intercept will be at x equals 3. So these are x-intercepts just using the null factor law. To find the y-intercept, we're going to make x equal to 0. So y will equal to negative 1 squared times negative 3. So that will just be positive 1 times negative 3 will give us a y-intercept of negative 3. So once again, we'll get a set of axes going. We'll put in all of our key points. So we've got one intercept at 1. That's really important to note that that's going to be our turning point. Another intercept at 3. And then we've got our y-intercept at negative 3. Oop, I just did the opposite of what I said. Make sure that you touch and turn. Okay, so this point here is a turning point because that factor was squared. Okay, and that would be my y-intercept. Now, I've just drawn this here so that you know it's a turning point, but when you present your final answer, you obviously don't write that. Okay, now for example 21, it says use a calculator to plot the graph of y equals fx, where f of x is equal to that. And then all we're doing is we're going to be looking at a series of transformations here. So just to try to figure out what's going on. Now, just by looking at these, hopefully you'll be able to tell what it is. You might want to pause the video and try to figure out what's going on here. But for this one, what we're doing is all of the x values will be moved over by 2 to the right. All the x values here will be moved to the left by 2. And here we'll have a dilation of factor 3. So all of our y values will be multiplied by 3. So what we can do now is jump onto our CAS calculator and give this all a go. So my CAS looks slightly different to yours on the iPad, but it'll be the same idea. So I've just got a page open here with the graph page. If you need to pause, go ahead. Otherwise, feel free to just follow along. So I'm going to type in the first equation, which is just x cubed minus 2x squared plus 1. Press enter, and you can see that this is the cubic that has popped up. So now for each of these parts, we can go ahead and add a new function. With your calculator, you can just press tab to get to that. So instead of having to rewrite the whole thing, I'm just going to write f of x minus 2. Uh, sorry, let's try that again. F2 of x is equal to f1 of x minus 2. Okay, press enter. And you can see that the whole function there, the one in red, has shifted over to the right by 2. We can then try that again. So f of 3 is going to be my initial function, except now it'll be x plus 2. Press enter. You can see that that has shifted by 2 to the left. And now finally, we've got our dilation of 3. So this one will be equal to 3 times f1 of x. Enter. And I will expect my original graph, the blue one, all the y values have been stretched by 3. So those are your three graphs with the different transformations. It's important to know how those can all be affected by your functions, but otherwise that is just the general idea of how cubics behave under different types of transformations. That's the end of exercise 4E.